video we're going to have a look at data, primitive data in particular within C++. The first part of it is really just going to look at how we can define it and the different types of primitive data that C++ makes available. To a degree, primitive data, I mean, this is basic stuff and for anybody who's learned about programming. It's useful, however, to look at it in C++, because it's safe to say that if you were to go about designing a new programming language nowadays, you probably wouldn't end up with the same overall structure to the data that C++ uses. And this is because when we're looking at how data was defined within C++, there's an historical context to it. And it's reasonably primitive. It's not particularly elegantly designed in terms of C++ primitive data, but there are underlying reasons why that was the case at a certain point in time. So we'll have a look at it. It'll be hopefully useful, certainly enlightening in terms of how data has evolved and changed over time. So we'll start off first of all by defining what exactly it is when we talk about a data type. I know fundamentally the programs we write, they're all about processing data. And we can think about data type having two necessary elements. The first one is a set of valid values. So if we're talking about a piece of data, we will refer to it by saying it has a certain type. It'll have a value, and that value will be valid for that particular data type if it's to be part of that data set. Importantly, alongside that, we also associate a set of operations, manipulations with those items of data. So these are the permissible things that we can do to it. So for example, for some types of data, the notion of addition, of adding them together to produce a bigger or a composite one makes sense. For other types of data, it doesn't make sense to say that you can add them together. So for data type, set of valid values and a set of operations associated with those valid values. For C++, similar to most other object-oriented languages, there's a distinction made between primitive data and then user-defined data, things like classes and objects, instantiations of those classes. So you can think of primitive data as the built-in data types that come along with rules set up on what constitutes valid values and sets of operations that constitute valid operations for them. They are primitive in the sense of they generally represent simple pieces of data. But alongside that, we have the user-defined data. This is our ability to create a user-defined class that will itself define what constitutes a valid value in that particular class range, and also define the operations that then can be applied to the instantiated data. We'll start off looking at the primitive data that C++ provides, and later on, of course, we'll look at the classes in a bit more detail. In essence, we're looking at numerical data types in terms of the primitive data. And there's two types, integer types and floating point types. And this gets into how we represent numbers internally inside memory. Ultimately, it's all ones and zeros, but we'll have certain patterns of ones and zeros, and we'll interpret them in certain ways as representing either an integer, a whole number, or a floating point, something with a decimal number. You can see down at the bottom, we have the non-exclusive list, but common operations that apply both to integer and floating point types. We can both add them, subtract them, multiply them, and so on. But you can see that not all of the operations actually hold between them. So some of the bit manipulation operations apply to integer types, don't apply to floating point types, and so on. Integer types, we'll start off having a look at those initially, then we'll go into floating point. There's actually a total of 9 different integer types that are built into C++. Pieces of primitive data. And you see a list of them down here. So at the top we've got char to short int, long int, to unsigned char to unsigned short int, unsigned int, unsigned long int, and we have a bool down at the bottom. The way of encoding these in terms of representation of numbers basically is the same between them. So what really differentiates these ones in large part is the amount of memory that they have associated with them in terms of number of bytes that we set aside to store one of those pieces of data. Three most common types of integer data are an int, an integer, as you might expect, a char, and a boolean. So char for character, bool for boolean. That's actually curious. And if you think about it, we're talking about an integer data type, a number, numerical value. So an int is definitely a numerical value. A char, a character. If we think about a character, if I ask you to name a character, you might say A, B, or C. They're not actually numbers per se. Or if I was to say, give me a Boolean value, you would say true or false. You're not going to say a number. So the fact that char and bool are wrapped up under the integer data types doesn't represent it from a user perspective in terms of how we think about data. It represents it from a modeling perspective about how inside a modern computer can you represent a character value or a Boolean value. We'll have a look at these now as we go through. For all of the other ones, the unsigned int, unsigned long int, and things like this, these are just basically different types of integers that can represent different sizes of numbers. So if you need to represent a big number, you'll use reserve more bytes of memory to do so. If you need a small number, you'll use, for example, a short or something like that to represent that, to use less memory. To have a look at these then, so ints are typically, they are whole numbers, no decimal points. Most C++ platform nowadays, if we think about an int, it is 4 bytes of memory that are set aside. Now, I say I'm going to talk about the limits file in the next slide, but this is something that has changed over time. Whenever I first was learning C++, ints were by default then in most platforms 16 bits in size. 15 years time, maybe ints will be 64 bits in size. So again, it's a thing that can change over time, and that's a characteristic of C++, but we'll talk a bit more of this in the next slide. So it is 4 bytes. If it's signed, you can go from roughly 2 billion to positive 2 billion. If you have a char, character, data item, single characters, alphanumerical or other, you have special characters like an exclamation mark and so on, they are represented, stored effectively as numbers. So this is where you have an encoding, where you can store a particular numerical value, and that corresponds to a certain character value. So ASCII and Unicode are the two common ones there. You can see your table over here for your ASCII table, that if you have, for example, the space character is hexadecimal 20 stored as a number. Boolean data then is either true or false. So conventionally, a 1 is true and a 0 is false. In terms of how the language works, 0 is false, and any other number, no matter what it is treated to be true. But again, it's how you represent true or false given fundamentally a numerical representation. The size of operator then comes into this here, and this is important because in C++ they define, for example, what a char is, what an integer is, but they do not, as part of the language specification, say that it must be of this particular size. Now this differs, for example, compared to say Java or C#, where there's a language specification that says an integer, an int, must be of this particular size. C++, that's not the case. There's actually a C limits file that defines just how big, for example, an integer is and so on. What it means then is in C++ you have a size-off operator. So you can use the size-off operator really with any type of data, be it, you see a few examples here, the type of data, an int, or if it's a particular instantiation of a piece of data. Now this applies to user-defined types, it applies to structs, it applies to primitive data, whatever you want. You can use size-off on it, and it will tell you the number of bytes of memory that are required to represent, to store that piece of data. That's useful for a whole range of different things in terms of how you structure and store things within memory, how you jump from one record to the next, and so on and so forth. The C limits file talked about, it is a built-in header file. And as part of that, it tells you just how big the maximum permissible size or lowest permissible size of a particular value is for it. So a few values here for Visual Studio. So the maximum signed character value, where like positive and negative values, is 127 down to minus 128. The maximum unsigned is 255, so that'll be from 0 to 255. So chars are obviously 8 bits in size. For shorts, or for unsigned short, you can see there the number range there are 16 bits in size. Ints are 32 bits in size. Now, this is where you have something a little bit confusing. So we've gone through from chars up to shorts to ints, and there's been a nice logical progression from 8-bit to 16-bit to 32-bit. If you're coming from Java, C#, and you're thinking longs, oh, they're 64 bits in size, as according to the language definition. C++, it does not require, the language specification does not require that a long is any longer than an integer. It requires it to be at least as long as an integer. And for most platforms, longs are still 32 bits in size. So an int and a long, for example, in Visual Studio, time of recording this, are both 4-byte values, 32 bits in size. There's no difference between them. If you want to go for a 64-bit integer, at the time of recording this, you need to go for a long. It's slightly confusing. It's not at all ideal. If you were designing a language, you would start off with a predefined set of values that should have a natural progression in terms of their size. It's not helpful in terms of C++ to have this, where you need to go and consult a file to work out just how big things are. And if you go an int and a long, you would expect them to be different. If they're exactly the same, they're not. Not ideal that you have a long if you want a 64-bit value. It's just the way the language has evolved. So over time, as processors can represent larger numbers, an int has moved from a 16-bit to a 32-bit value. Whenever that shift happened, ideally a long would have doubled out to 64 then, but that wasn't the case. Signed and unsigned values, you can read a little bit about them on this side. As you might expect, if it's a signed value, you're allowed to have positive and negative values. If it's unsigned, then it's 0 up to some large positive value. It depends on what you're doing. A long time ago, sometimes it was important, or it was more important than it is nowadays, to use unsigned values, because then it gives you a wider positive range of numbers that you could represent. But nowadays, generally doesn't make that much of a difference. Floating point types then is the next area. So for floating point data, we have 3 types defined within C++. They're float, double, and long double. Floating point, it's something with a point in it, a decimal point. So 4 is a integer, 4.0 is a floating point value. So anytime you get a decimal point appearing, even if it's followed by a 0, that is a floating point number. C++, as mentioned, you could float, double, and long double. Now, you might be hoping here there'll be a bit of consistency with the integers in terms of the size of these things. You're going to be disappointed. Double, sometimes referred to as a double precision number. Float, sometimes referred to as a single precision number. They're probably reasonably well named. So most platforms, certainly C++ at the minute, float is 32 bits in size. Double is a 64-bit floating point number. Long double, is it any bigger? Sadly, it's not. It's also 64-bit in size. So there's no reason at the minute to use a long double in comparison to a double. You can see the size here. So if it's a float, for a double or long double, again, you get better precision with using a double point floating point number as compared to a single precision floating point number. That is important. You're not sort of necessarily increasing the range of numbers, though you are. You are also increasing the precision of the number. So floating point numbers always have a degree of inaccuracy about them in terms of the precise values that they can represent. You can't magically represent anything over this range, because under the surface you're still representing these as a single, as 32 ones and zeros. So there's a finite number of discrete floating points that you can represent. They're not uniformly spread, they're more densely packed around 0, and then they become less densely packed the further you go away from 0. For literal values, so a literal is just an actual instantiation of a particular precise value. So 4 is an integer literal. 4.0 is a floating point literal. If we want it to be precise, and we can be, to say if this is a float literal or a double literal or a long double literal, there are ways of doing that, and you can see the examples there where you follow the number with a letter suffix that tells you what type of literal it is. So 3.14f is a floating point literal, 3.14 is a double literal. And most cases, it'll autocast from one to the other. Not in all programming languages, though you may need to be explicit in terms of your type assignment. Takeaways in this, there's only a few of them. C++ possesses a good number of different types of primitive data. The reality is you only need the common ones in terms of ints, or floats, or doubles, or chars, or booleans, and or your long if you need a particularly big number. So only a small subset are commonly used, and again that reflects evolution over time. 30 years ago, C++ would have been used across a much wider range of physical devices, CPUs, which differed a bit in their architecture, or differed more in architecture than maybe it does nowadays. So there was more of a need to have these different representations. So other data types become less relevant over the years or have more specialist uses. But it's useful to understand why they're there. It's an historical context, and that some of the reasons why they made sense in the past do not persist nowadays. And that's going to be often a common story in C++, and it's part of the reason why C++ 11 tidied up the language so much. But it does maintain this backwards compatibility, which results in some of these slightly inelegant aspects still being retained.